Hello guys, let's continue our discussion about the calculation of viscosity using the wall method. Now let's define the force field at how the atoms are going to interact. This is done using the pair style command. So pair style command is defined here, and its syntax is pair style with the style, and that is LJ cut with the cutoff distance for calculating the interaction between pairs, and this is calculated using the 12-6 Lennard-Jones potential. Potential requires coefficient to be defined, and this is defined using pair coefficient command, and its syntax is pair coefficient and the atoms I and J. But here it is written as stars. Stars means the interaction between all atoms, every other atoms. So star for all atoms, while the arguments are energy and distance coefficients required for the LJ potential, which are 1 here. Okay, now finally come to the run section. Here we will discuss about various operations within the time steppings. So important commands are the computes and fixes. Okay, let's compute temperature of flow group by using compute command, whose syntax is compute and ID of the compute and the group ID of on which the compute will be implemented, and the style and arguments. Here we will compute the temperature of the flow group. So we will name it the flow. We will work on flow, and then the style is temperature, temp, only temp word. This means we will calculate the velocity of flow group, not the velocity but the temperature of the flow group. Okay, now update the position and velocity of the whole simulation system using the NVE ensemble, which assumes energy, volume and number to be constants. So let's write some comment also. Update position and velocity. For that we use fixes for that, and this is going to be our first fix, and we name it also the first one, and we apply it on all atoms, and then we mention the ensemble, that is going to be NVE, and let's move on. Okay, now next we define the thermostat, the flow region, using the compute with temperature and partial style. Okay, now let's compute the temperature of the flow region. I name it thermal, and it's the flow region, and I like to calculate the partial temperature, and it is satisfied with temp partial, and want to calculate temperature contribution from y direction only, because temperature is linked with the kinetic energy, and kinetic energy is defined with the help of dimensions and velocity. So we want contribution from y direction only. Okay, so as our system will move, atom will exert forces on the wall group which we have defined. It do not have a particular aim, but wall is used for shearing purpose only, for shearing the flow group. So fluid is Lennard-Jones fluid is moving in one direction, and the upper wall is used for just shearing the fluid, so that we may able to calculate the viscosity. So the walls, so the forces exerted on the walls and by the walls are not required for calculation of the viscosity. So we need to nullify those forces. But before that, we also need to calculate the we also need to implement the fix Langevin, and this is going to be second fix, and it will be applied on the flow group because we want to thermostat the flow group. So that's why we need to apply the Langevin style with the 1 meaning starting and ending temperature with a damping factor of 0.1 and a random seed. Now we can set the forces to the 0 because now we will use the fix command, third fix, and that will exert on the wall region, and we use the style set force, and we mention that we don't want forces for this group. Okay, so there will be no forces in the wall groups atoms. Let's also correct the fix number 2. We also want to modify the second fix, and its style is going to be fix modified. So the contribution from the partial temperature is going to be thermostated with the help of a second fix. Okay, now next we do spatial binning. Spatial binning will be done using the chunk atom style of the compute command, and we will do the one-dimensional binning because we are interested in calculating the viscosity in the y direction. Okay, we will use the compute command, and the name of this command is going to be layers, and we apply it on all, and the style is going to be chunk per atom, and we will do spatial binning in one dimension, and the dimension is going to be y, and the spatial binning will start from the center with the delta of 0.05 in reduced units. So this binning requires a dimension, which is the y here, and the size of the bin is controlled with the delta argument, and that is 0.05 here. Binning can be started from the start upper and lower region, but here we are starting it from the center, and it will go towards the upper and lower region. And simply we are making layers along the y-axis and assigning IDs to those layers. Then any atom coming in a bin is assigned a respective ID. By ID I mean chunk. We are chunking the layers, and we are assigning atoms in that chunks to that chunk number. Okay, next with the help of average chunk fix command, properties of atoms in each chunk is calculated and averaged. And the command syntax is as follows: fix, we use fix, and this is going to be fix number 4 and applied on all, and the style is going to be average chunk, means we want to calculate the average properties per chunk. And what we need to do is we need to pass 3 numbers. Let me just write these number and then I will explain to you what these means. 500 and 10,000. Actually the syntax of this command is fix id, group id, average chunk, n every, n repeat, n frequency, and chunk id, and so on, keyword and arguments if required. It simply means after defining the average chunk, it simply means after how many time steps chunk inputs need to be taken, which is 20. Means after means take the chunk inputs after every 20 steps, 20 time steps. Then the mentioned number is 500. It means it means that take this value 500 times before calculating average. After every 20 time steps, take the values 500 times before calculating the average, and finally average after 10,000 time steps. And chunk id is the layers compute, means of what chunks we want to calculate, and this is going to be layers, because we have defined the compute layers which calculate the chunk IDs, which define the bins and assigns the chunks, and this is where we want to average the chunk property. Okay, we can also provide other keywords and arguments, like we can give the velocity in the x direction and write it to the file and name it profile dot wall dot 2d. And finally we apply the fix number 5, and that is applied on all atoms, and it does nothing but enforce the simulation to be 2D. Okay, now let's define the next important part of the run command, and that is the equilibration. After defining the atoms and giving them some velocity and also sharing them, let's allow to equilibrate the system, and for that and compute some temperature and the values for the flow group as follows. First I will define a variable that I can also define up, but I like to keep it here because it's more relevant here, and the starting sections just is relevant to the starting variables. So here I will define the y box variable. It is the length of the y, and that is going to be equal to the lattice parameter in the y direction, y lat, times the y dimension, and I will write it with a dollar. Okay, that will be the y box, because because the dimension of box from till the 20, we have defined the y as 20 in the and units in the box, and the lattice parameters in that direction. We will multiply with the lattice parameter with the 20, and we will get the length of the y box, because we are doing this with the y side. Next we use the another compute with the style temp ramp. and its syntax can be written here like compute, and we name it tilt, and we apply it on the flow group and with the style temp and ramp. It is used to calculate the temperature after subtracting the ramped velocity and we can print it to the screen using the thermo command. Okay, we start with the Vx. In the extraction, we subtract the velocity from the in the V extraction. We start from 0 to the 2.7 shear rate, and from Y 0 to the box length, and that is we have just defined the Y box variable and in units of box. Okay, let's print the inputs after 1000 time steps, and the input that we want to see is defined with the thermostyle, and thermostyle is going to be custom, that we want our custom input, and that is we want to see step number, temperature in that step, and the compute tilt value, because it will show us the tilt value, and as it is a ramping, so we write the compute and we write its name next to see if I can spell it right. Tilt. Okay, and then comes the E pair energy, and the total energy E total, and the pressure XY tensor, and then we run it for some time. Run it for 1000, maybe 1000 and 10,000. This will depend on a particular application, because you need to decide how your molecules or atoms are going to be relaxed. Is that run number of runs are enough? This will be defined with the help of time step and the number of runs, that either the whatever units comes in, either the femtosecond relaxation is enough for equilibration or not. So you run for these number of steps, and then you calculate your data, and data can be calculated. Let's name this section data gathering run. Okay, now you have equilibrated your system. 10,000 is not enough, but it is okay to use it here, as it is just a tutorial, not a real world application. So you can adjust your runs according to your application, but for now just run it. And I will define the variable viscosity. Again, I am defining it here because it makes more sense to write it here instead of writing above. And its name is, I am defining viscosity, and it's going to be equal to the pressure tensor in the XY, and then it is going to be divided by the variable Vs rate. I need to see if I have defined the S rate above or not. Okay, I need to define it here, variable, and that is going to be S rate equal 2.7, because this will be the ramping velocity. So we will increase velocity from 0 to 2.7. so this is a variable instead, and we divide it with the S rate, and we divide it with the length of the Y. This is defined our viscosity for the wall method. So we want to show this value, average value, on the screen as well. We can define it, we can calculate it first with the help of fix command with the average time. This will average with respect to time, takes after 1000 and take one value and just print it to the screen. And the variable that is going to be displayed is variable viscosity. Yes, and average is going to be running. Okay, let's also define our thermostyle that is surely custom. And what we want to see is step number, step. We also want to see the temperature and the pxy tensor, and of course viscosity variable with the running average. And I want to see the temperature to be tilt temperature, the temperature of the tilt compute, the temperature that is at the time of shearing, and temperature will be tilt. Okay, now let's write one last command, that is dump command. Dump command I am using to just dump the video so that we can see the simulation in video. It is done with the name applying on all atom, and style is going to be movie, and it will be taken after every time step, and the format is going to be movie dot avi. You can select your format here, and its size also 640 by, let's say, 480. And after dumping the video, you run it, and now it will run. It is equilibrated. Now it will run for certain time. The time step, the runs you mentioned, let's run it for 1.1 million steps. Okay, and collect our video, and let's discuss the results in the next video. See you guys in the next one.